Good morning. In the previous section, we have discussed regarding the induction motor drives. So we have discussed the voltage source inverter control of a induction motor. So in that case, so whatever the VSI is there, it is operating in two states. One is stepped wave uh, converter mode, and the second is pulse width modulation. So we have seen the operation of that VSI in the previous section. So by using that VSI also we can control the speed of the induction motor. So that VSI control and the cyclo converter control and the third, the closed loop control of induction motor will lie or will come under the category of voltage uh, and frequency control of induction motor. So in today's section, we'll discuss the cycloconverter control of induction motor and second closed loop control of induction motor. So again, I'm going to share some of the documents, so which mainly uh, give the information over today's topics. So in this case, first we will see the cycloconverter uh, control. So here, uh, by using the cycloconverter control also, we can control the speed of the induction motor. So what is cycloconverter? So a cycloconverter is a converter which mainly uh, converts the fixed AC voltage, fixed frequency into the variable frequency, variable voltage without any DC links. Without any DC links. So this cycloconverter mainly converts the particular constant or fixed uh, variable fixed frequency or the fixed voltage into the variable frequency variable voltage supply. So in this case, here we are having the half wave cycloconverter fed induction motor. So this is the diagram for the half wave cycloconverter fed induction motor. So in this case, uh, whatever the halfway cyclo converter is there, so in this case the three-phase power supply is used to control the speed of induction motor. So normally we are using three-phase power supply, so which is used to control the speed of induction motor with the help of the cyclo converter. So again, I have shown in this particular figure, uh, the three-phase cyclo converter is supplied with a three-phase supply, and the function of this cycloconverter is which converts mainly the fixed frequency power supply to the variable frequency power supply. So by varying the frequency of power supply, we can control the speed of induction motor. So hence it is called as the frequency control method. So in the to three phase, uh, the three phase converter generates mainly the three phase output that is fed to the induction motor. So again, in this case, whatever the output voltage waveform is there, so whatever the output we are getting at the particular motor, so it is having some of the harmonics, but it is close to the sinusoidal. It is close to the sinusoidal, and hence the leakage inductance is used. Here we are using leakage inductance in each phase to minimize the direct derating and torque pulsation of the motor. minimize the direct rating and the torque pulsation of the motor. So again, the drives has regenerative braking capability. So again, full four quadrant operation is obtained by reversing the phase sequence of this motor terminal voltage. So since the cycloconverter employs large number of thyristors, so it becomes economically acceptable only in large power drives. In order to have the particular switching operation, we are considering here some of the thyristors. Just by changing the particular switching operation or the particular firing angle, we can get the different uh, outputs. So again, this particular cyclo converter is having some of the advantages, uh, where this particular cyclo converter, uh, it is V and EF controlled, so we can control the voltage as well as frequency. Again, this is having a smooth operation at low speed. At low speed, again, high power output. Whatever the power output at the particular converter is there, it is high, and it is four quadrant operation. We can operate in all the four quadrants. Again, good dynamic response. It is having good dynamic response, and then only one conversion stage. So there is no maximum conversion stages. Only one conversion stage you can have. Again, coming to the disadvantages of this particular cyclo converter, harmonics increase with the F. Again, speed up to 40 percentage of the synchronous speed, only suitable for large power drive, poor power factor at low output voltage. Applications we can use in cement plants, conveyor drives, and then diesel electric locomotives. So these are some uh, applications of cyclone. So now next we will move to closed loop speed control of the induction motor drive, of the induction motor drive. So in order to have this particular closed loop speed control, again it is fed from VSI, voltage source inverter. So this is the next topic. It is closed loop speed control of induction motor fed from voltage source inverter. So this is the particular block diagram of this particular. Again, by means of this also we can control the speed of the induction motor. Speed of the induction motor. So now, uh, whatever the uh, control scheme is there, it is only to automate uh, again the open loop control. Whatever we have seen in the VSI and CSF at induction motor drives. In order to automate the open loop control, we are using this closed loop. So then how to automate speed control? So means that it is not essential to control the firing angle, duty cycle and time period of inverter every time for required speed. For required speed. So if this closed loop control makes us that the required speed, what is needed to be operate the induction motor, will be set as the reference, will be set as the reference automatically. The entire closed loop function, and it adjusts the speed of the induction motor. It adjusts the speed of the induction. So here, coming to this particular diagram, so we can see this particular motor here. We can see this motor. The speed of this particular motor can be controlled. Can be controlled. So starting from here. So this is an induction motor. We have plotted this for an, let us say, on line diagram. Line diagram. So this is an induction motor which is again fitted to PWM inverter. This is the PWM inverter. So this is motor. It is fitted to the PWM inverter. So under VSI, under VSI voltage source inverter, you remember it is connected to PWM inverter. It is connected to the PWM inverter. So PWM inverter is having capability to control voltage and frequency internally. So why we are connecting it to the PWM means we are using PWM inverter because PWM inverter is having the capability to control voltage and frequency internally. So now just looking at this particular diagram, there is no external voltage control is required in this particular PWM. There is no external voltage is required, so that directly DC supply is uh, connected to PWM inverter. So this DC is connected to the PWM inverter, and between the DC supply and input of the inverter, we connected one LC filter. It is LC filter. This is to remove ripples in DC supply. So after rippling out DC supply, we are connecting that to PWM inverter. So this is connecting to the PWM after removal of the rippling. Now this fixed DC voltage is given to the inverter. It will adjust the variable output voltage, variable frequency, so that it maintains constant voltage frequency ratio. So again, but what are the based for adjusting the frequency and voltage? On what basis it has to adjust? So that is the question. So there are the basis on the magnitude of this modulation index and frequency. So now we come here. So there are mainly the basis on the magnitude of this modulation index and the frequency. So now there are two control input for PWM inverter. Based on these two control inputs, M and F. So it can adjust the voltage and frequency. Depending on this particular. So voltage variation will be from modulation index M. Voltage will be from modulation index. Again, it is connected to the controller. And frequency variation based on the frequency control. So this frequency is based on the frequency control. Now, these two are major two functions. These are the two major functions. So if we have the constant value of modulation index, let us say we have constant value of modulation index and frequency for the inputs for this, then this will not at all control. So if you vary these two quantities, M and F, and it will control both voltage and frequencies. So whenever we require that control. So how to adjust the modulation index and how to adjust the frequency? So these two are based on the required speed, where we need to operate this induction motor. Again, particular whatever the M and F are there. So the how to adjust this particular is the question, and these two are based on the required speed where we need to operate this induction motor. So actually this induction motor is initially running with the some speed, let us say it is initially running with some speed, say omega m, you can say. So that is speed is sensed by a speed sensor, This is the speed sensor we are using, or it may be a tachometer you can use, or tacho generator, what we have here. So now, so the tachometer will sense the speed of this three-phase induction motor that we are treating as omega, that we are treating as omega. So omega m is referred as the mechanical speed in radian per second. So this is actual running speed of the induction. Now, and the required speed where I need to operate this induction motor, I am setting as omega m star, omega m star. So this is, let us say, this is the particular omega m star. So this is the reference speed. This is the reference speed. So this reference speed is says that induction motor required to operate at this particular speed, at this particular speed. But its actual speed is omega m. Its actual speed is omega m. If these two are equal, no worries. If these two are equal, no worries about this entire scheme. Directly, the induction motor operate at the previous speed only. Previous speed only. If these two are not equal, if these two are not equal, there is some difference. There is some difference. So the required speed is different than the actual running speed. So it is again compared at this particular comparator, and based on these polarities, it will take the difference. It will take the difference. So like omega m star minus omega m, that will become speed error. So whatever the e omega m is there, it is called as speed error. So again, this speed error will be processed through a PI controller. This is processed through PI controller or speed controller. Because I am processing here a speed error, hence I am calling this PI controller as speed controller. So this PI controller now will produce a slip value which is required proportional to this speed error. Again, this is producing a slip value which is required proportional to this speed error. So now, whatever slip value which is produced here is again passed through the slip regulator. This is the slip regulator. So we need to know that why slip is produced here. So again, instead of voltage or current from the PI controller, so why? Because the speed of induction motor is controlled. So based on the controlling a slip quantity, as you recall the expression, that is whatever NR is there, NS into 1 minus S, NR is rotor speed and NS is equal to synchronous speed. So the synchronous speed will not vary again. And next, by taking 1 minus S, so this 1 is also constant. So if you regulate the slip value, the rotor speed is again varied. So why we need to take a slip is because, so whatever the slip is there, it is, we can vary that particular slip. So if you regulate the slip value, rotor speed is varied. Means that hence here my intention is to regulate the speed in order to regulate this particular speed. So regulate the speed in the sense it is depending upon the slip value. So the slip is produced at the output. So likely I am setting the function of PI controller. Likely I am setting function of PI controller so that the speed error is having proportional slip value. Again, whatever the speed error is there, it is having proportional slip value. And from this PI controller, from this again, whatever the PI controller is there, so now this is passed to the slip regulator, So the function of slip regulator is that, please remember, the function of this slip regulator is that the value of slip produced by PI controller, that is speed controller will be see that it should be under the limits of actual slip value. So whatever the value which is developed or the coming out of the speed controller is there, will be see that it should be under the limits of actual slip value or not. So now actual slip value in the sense we have 0 to 1 for the motoring action and 0 to -1 for the generating action. So means that either your motor has to function below rated speed, let us say it is motoring action, or above rated speed it is generating action. So in order to know that whether the motor is operating again either uh, below the rated speed or above the rated speed, so it ensures that slip regulator having uh, the saturated function, whatever the saturated function is there. So it is again going to one level. Again, it is reaching to the saturation, and again, same value of slip will be there, and then again after it is uh, coming in the negative direction. So this saturated value is plus one, and in the negative direction, if you come here, it is -1, and it is having value of -1. It means that it always sees the value of slip should be under the limits. Suppose it is exceed the value of 1, so this slip regulator so will limits the value of slip to 1, and it will pass if it is under the limit of -1 and +1 and +1. So it will not function now. It leaves the value whatever it is produced at speed control. So that is function of slip regulator. So it will adjust or it will limit value of slip under the -1 or +1. And also slip regulator will produce the proportional value of slip speed, and this what it is, we says that omega s dash, omega s star. So this slip speed value is compared with this particular operator uh, with the actual operating speed of the induction. So now how much speed is slip back now? So actually we are giving a reference speed. We are giving reference speed. Here speed error is generated. Speed error is generated. Let us say this is the speed error, and slip is generated. Slip is generated, and slip regulator is controlling the slip value. This is controlling the slip value, and slip speed is set. Slip speed is set now, and this slip speed is having small value. Slip speed in the sense we can say that S ns, S into ns. Slip speed in the sense it is S into ns. Here is we are having uh, SWS. So now S value is very less. We know that whatever the S value is there, so it is very less. So we know that WS multiply in the sense that value again small. So this is the slip speed, that is omega S star, that is again means that this value of speed needed to be adjusted. Omega star needed to be adjusted. So that is function of this particular uh, uh, controller, speed controller. So now we have omega S star and omega m, omega S star and omega m. So this omega S star, it is again slip speed, and omega m is what your actual speed. So these two are compared. These two are compared here at the comparator. So and required speed is needed to be adjusted. And required speed is needed to be adjusted. And is set here as omega s. Set here as again omega s. So now what we need to do is this omega s, whatever the omega s is there, so this omega s is having the function of frequency. So whatever the omega s is there, so it is having the function of frequency, and so that the proportional frequency is adjusted here. Thus proportional frequency is adjusted. So based on this omega s, the frequency is adjusted as one of the input to the PWM inverter. PWM inverter. And the same thing, this omega s is to be crosses through the flux control. Flux control. So why it is crosses through the flux control? In the sense, generally, if you look at the operation of induction motor, uh, voltage is given as the input to the induction motor. The flux produced in the induction motor stator is proportional to the voltage that is given as input. So the again, whatever the uh, magnitude of voltage is there, it is decides the amount of flux set up in that stator. So that here it is we are doing reverse. We are doing the reverse. So means that we are producing the proportional voltage. Again, we are producing the proportional voltage for the existing flux here, for the existing flux in the induction motor. In the induction motor. Now here I am taking, let us say omega s, omega s as the input, and this what the speed needed to be adjusted based on this flux, based on this particular flux. So how much voltage is required, that is I am setting as voltage reference, let us say v star. So this flux controller will produce output as voltage reference v star. Again, it will produce v star. So next, actual operating voltage of the induction motor by using voltage sensor, that is uh, whatever the voltage sensor is there, we are having this particular voltage sensor. So the next actual operating voltage of the induction motor by using voltage sensor, it is sensed from the again terminals of the input of the induction motor, terminals of the input of the induction motor, and it is again uh, as actual operating voltage of the induction motor. Again said here the voltage are compared. So whatever the voltages are there, so they are here compared. Reference voltage and the actual operating voltage, and these two voltages are given. These two voltages are given and compared at the comparator produces the voltage error. Again, the produces what, the voltage error. So now, again, this voltage error is processed through a voltage controller. Voltage controller. This voltage controller will set up a magnitude of modulation index M, where it is needed to be operate, where converter is needed to be operate. So based on this modulation index M, the voltage output of this inverter output is varied based on frequency input. Uh, the output frequency of the inverter is varied. Output frequency of the inverter is varied. So both voltage magnitude and frequency of magnitude of inverter depends upon the two, that is M and F control inputs. So two closed loop again. So this closed loop operation is continuously performed, until it is required to operate at this particular uh, until it is comes to this speed, that is omega m star. So that voltage varied, frequency varied. So that voltage varied, frequency varied, and constant v by f speed control is happens. Constant v by f control is happens in this particular case. So this is about the operation of this closed loop speed control of the induction motor. So in the next class we'll discuss regarding the CSI.